Imagine that f is some function of x, and that a plot of f of x versus x is given by this green curve. As I discussed in a previous video, the derivative of f of x with respect to x is the slope of the f of x versus x plot as a function of x. So the point is this. The derivative of a function is itself a function. So that may lead us to ask this question. What function is f of x a derivative of? So let's imagine writing f of x as the derivative with respect to x of some other function of x, which I'll call big F of x. So I've got little f of x, which is the derivative with respect to x of big F of x. So if little f is the derivative, what is big F? Well, we can call big F of x the antiderivative of little f of x. Before we go any further, let's discuss antiderivatives. As I noted in a previous video, the definition of the derivative, right here, can be used to derive shortcut rules for taking derivatives of specific kinds of functions. For example, this one, which tells us that the derivative with respect to x of x to the nth power is equal to n times x to the n minus 1 power. Of course, every derivative formula is also an antiderivative formula. If we take this as our starting function, then this is the antiderivative. However, that's not a very satisfying antiderivative rule. This is not really a nice starting function. This is really just kind of an ugly way to write a function in the family of x to the power of n. This leading n out here is a constant. We have x to some power. Why not call it x to the n? What we would really like is a formula to find the antiderivative of x to the n. So let's try to do that. That is, we want a function that if we take the derivative with respect to x, gives us x to the power of n. So we can either try and do this by trial and error, or we could try to run the derivative process in reverse. Let's try running the derivative process in reverse. So to run the derivative process in reverse, let's first spell out what this derivative process is for this particular formula. So the first thing we do when we're taking the derivative with respect to x of x to the power of n is the n exponent comes down. And then we decrement the exponent by 1 from n to n minus 1. So if we were to run an inverse process starting with the end and going back to the beginning, what we would do is we'd start by incrementing the exponent by 1, which means taking x to the nth power and raising it to n plus 1 power. And our next step would be to do the inverse of this process. So instead of multiplying by the exponent, we would divide by the exponent. So let's divide this by n plus 1. And now that we've done this, we should check to make sure we haven't outsmarted ourselves and make sure that if we take the derivative with respect to x of this, we get that. So now let's apply the derivative rule for x to the power of n and see that we actually get this result. So the first part of the derivative rule says to multiply by the exponent, which is now n plus 1. So if you multiply this by n plus 1, that'll cancel this n plus 1. And then the second part of this rule says to decrement the exponent by 1. So we would take it down from n plus 1 to n, and it looks like it works. So now we have a nice antiderivative rule. The antiderivative of x to the n is x to the n plus 1 divided by n plus 1. Before I continue, I need to make one more really important point. Antiderivatives are only defined up to an arbitrary constant. Remember, the derivative of a constant is 0. So if I go back here to my original expression defining the antiderivative, I could add a constant to f of x, and it wouldn't change this at all. Just to make this explicit, let's let capital G of x equal capital F of x plus a constant. Now let's take the derivative with respect to x of both sides. And on the right-hand side, I've used the rule that a derivative of the sum is the sum of the derivatives. And then right here, we have a constant. Derivative of the constant is 0. And so we see that the derivative with respect to x of capital G of x is the derivative with respect to x of f of x. So if capital F of x is an antiderivative of little f of x, then capital G of x is also an antiderivative of little f of x. So if you have an antiderivative, you can get another antiderivative of the same function by just adding an arbitrary constant. So let me update this formula to say that. Having discussed the calculation of antiderivatives, let's now look at the graphical interpretation of the antiderivative. That is, given a plot of little f of x versus x, how do we connect this plot to the antiderivative of little f of x, which is big F of x? To look at that, let's multiply this equation on both sides by little dx, and we get little f of x times the infinitesimal dx equals d big F of x. That is, an infinitesimal change in our antiderivative function, big F of x. To see what this means on the graph, let's look at this. So for a given value of x, little f of x is just the height of the f of x versus x curve above the x-axis. Little dx is just a run along the x-axis, which I can label here. Keep in mind that little dx is an infinitesimal, but I've made this line longer so that we can see it. So it looks more like a delta x. All right, so this width dx and this height, little f of x, defines a rectangle. Looking at this rectangle, we see that its area is approximately equal to the area under the f of x versus x curve in the region from x to x plus dx. The only difference is this little overlap region right here. But remember, dx is really an infinitesimal. I've drawn it more like a delta x. But if we imagine squeezing delta x down in the limit where delta x approaches 0, which is really what we're doing when we're thinking about a dx, this overlap area also approaches 0. And it turns out we don't need to worry about it at all. So the area under the f of x versus x curve from x to x plus dx is equal to the infinitesimal change in our antiderivative function f of x from x to x plus dx. So if that's true for an infinitesimal, and it's true for the next infinitesimal and the next infinitesimal and all the prior infinitesimals, then it should also be true from, say, going from x equals a to x equals b. That is, the area under the curve from x equals a to x equals b should be equal to the change in our antiderivative function, capital F of x, from x equals a to x equals b. And let's write that up here, where big F of x evaluated at b minus big F of x evaluated at a gives you the change in big F of x from x equals a to x equals b. And again, that is equal to the area under the curve. OK, so now we need a way to express this area under the curve of f of x versus x from x equals a to x equals b in terms of our function little f of x itself. To do that, let me just replicate this rectangle and fill all the space between x equals a and x equals b with similar rectangles. Now let me write an expression for the area of these rectangles right here. To understand this expression, this is a shorthand for writing out a sum of 7 terms. So instead of writing out all 7 terms, I can write them here. F of x sub n, delta x sub n, and I can let n go from 1 all the way up to 7. So if I were to write them all out, I'd have 7 terms ending with f of x sub 7 times delta x sub 7. Each of these terms corresponds to the area of one of these 7 rectangles. So here's x1, x2, x3, x4, f of x1, f of x2, f of x3, f of x4, delta x1, delta x2, and so on. So f of x1, delta x1 would represent the area of this rectangle. F of x7 times delta x7 would represent the area of this rectangle. And I've reverted from dx back to delta x because I've shown some larger increments here. So the combined area of these 7 rectangles I've drawn is an approximation to the area under the f of x versus x curve from x equals a to x equals b. We have overhang here, here, and here, and here, and here, and some underhang there and there. Now, in the limit where we take our delta x's and squeeze them down towards 0, which is really what we're doing when we're thinking of dx's, those overhangs or underhangs all shrink. We can visualize that. Imagine instead of having 7 rectangles, we had 1,000 rectangles. I can't make that change here, but I can make that change here. Now, if we packed 1,000 rectangles in here, all the delta x's would necessarily be much smaller. And these overhangs would be much smaller, and these underhangs would be much smaller. And we have a much better approximation. But why stop there? How about we imagine n rectangles, and then imagine taking the limit as capital N approaches infinity? Well, as we pack ever more rectangles in here, the delta x is going to get smaller and smaller and smaller and smaller. And in the limit, as the number of rectangles approaches infinity, our delta x's are going to shrink down and approach 0. So the limit as capital N approaches infinity is equivalent to the delta x's approaching 0, which is really what we're imagining when we're talking about dx anyway. It can be rigorously shown that in the limit, where the number of rectangles approaches infinity, or equivalently, where the delta x's squeeze down and approach 0, that the overhang and underhang issues completely vanish. And therefore, that this infinite sum of infinitesimals, as n approaches infinity, is exactly equal to the area under the curve, under the f of x versus x curve from x equals a to x equals b. So this, with n approaching infinity, gives us our expression for this area in terms of our original function, little f of x. Now, this is sort of a tedious thing to write out. We need another way to write this out, and I'll do that right here. And this expression, finally, is an integral. This is read as the definite integral of f of x, and by that I mean little f of x, from x equals a to x equals b. So this integral is a way to write this sum as capital N approaches infinity. This squiggly symbol here, the integral symbol, is actually an elongated s. That's its origin. Does this mean that if you encounter an integral that you need to rewrite it as a sum with a whole bunch of terms? No. We go through all this to give you this. And then we can use the fundamental theorem of calculus. So if we need to calculate the definite integral of some function, little f of x, from x equals a to x equals b, all we need to do is compute the antiderivative of little f of x, that would be big F of x, and then evaluate the antiderivative at the end value of x, x equals b, and the beginning value of x, x equals a, and take the difference. Beautiful. So before I close, I need to make a few more quick points. And before I do that, I'm just going to erase some of this board. First, an integral with limits like this is known as a definite integral. There's also something called an indefinite integral, and that's written without the limit signs. And that's really just a way to express antiderivative formulas. For example, so this expression says that the indefinite integral of x to the nth power dx is equal to this. Or equivalently, the antiderivative of x to the nth power is this. Normally, antiderivative formulas are written in terms of indefinite integrals rather than in terms of derivative expressions. So this reminds us that the antiderivative of a function is only defined to within an arbitrary additive constant. So then we ask the question, which antiderivative do you use when you're evaluating an integral? Well, the answer is it doesn't matter, and I can show that. Imagine that big G of x is big f of x plus a constant. If big f of x is an antiderivative of little f of x, then big G of x is also an antiderivative of little f of x. So imagine that instead of using big f of x as my antiderivative for little f of x, I used big G of x instead. Would that change the result? Well, let's see. So this expression would become, if I used big G instead of big F, and now I can make this substitution and rewrite it. So big G of b would become this. And big G of A would become this. Now if I distribute the minus sign through, these C's will cancel. And I get, in other words, if I'd used big G instead of big F as my antiderivative for little f of x, I get the same result anyway. So you can use any antiderivative of your function that you're integrating as long as you use the same one at each of the limits. I want to make one more minor point relating to notation, and that's there's a shorthand way to write this. So this is defined to mean this. So if you see this, a function followed by a vertical line and symbols at either end of that line, it means take the function and evaluate it at the top symbol, and then subtract the function evaluated at the bottom symbol. That's what that means. So that's pretty much it for the theory portion of my introduction to integrals. I'll do some example problems in a separate video. Thanks for watching, and see you next time.